Moments arrive in the unfolding story of humanity when the fabric of the known universe seems to tremble, whispering truths so vast and unforeseen that the foundations of our understanding shift profoundly. One such epic-defining instant occurred precisely at 410 Universal Time on the 24th day of the 10th month in the year 2025. As slumber enveloped the majority of the globe, a quiet vigil was kept in the vast, arid expanse of the Karoo Desert within South Africa. There, 64 immense radio dishes, part of a singularly remarkable scientific instrument, stood sentinel. Their surfaces were tilted towards an exceptionally challenging sector of the sky, perilously close to the blinding radiance of the sun itself, an area where observation approached the realm of the impossible due to the overwhelming glare. This sophisticated array, the Murchison Wide Field Array, one of humanity's most exquisitely tuned instruments for cosmic listening, was executing its fundamental purpose, attuned to the faintest echoes resonating across the immensity of space. As we contemplate the enigma of 3IATLAS, I invite you to consider your own vantage point. In which city do you find yourself watching this unfolding narrative? Feel free to share your location below. Furthermore, I pose this question with genuine curiosity. Have you ever witnessed something truly anomalous unfolding within the vastness of the sky above you? And then, in that desolate desert dawn, the listening array registered a signal utterly alien to its expectations. Within its meticulously recorded data stream, two distinct absorption features materialized. They were faint, whisper-soft against the ever-present background hiss of the cosmos, yet they possessed an unmistakable structure, a pattern suggesting deliberate design rather than random chaos. The frequencies at which these features appeared were astonishingly precise. One at 1,665 MHz, the other at 1,667 MHz. If you possess even the slightest acquaintance with the field of radio astronomy, these specific numbers should resonate with immediate significance, sparking a surge of recognition. These values constitute the well-established spectral fingerprint of hydroxyl radicals, the OH molecule. This chemical signature is a telltale indicator, appearing distinctly when molecules of water are fractured apart by the intense, harsh ultraviolet light bathing the region. This was no mere artifact of static. This was not the fleeting interference caused by a satellite traversing the field of view, nor a simple malfunction within the complex instrumentation.
During this remarkable episode, chemical signals were transmitted across vast expanses of the cosmos, spanning hundreds of millions of kilometers of boundless emptiness. These signals originated from an entity that was unaffiliated with our own solar system. This celestial being, known as 3IATLAS, had been given its name after it was discovered earlier that year. The letter I in its designation signified its interstellar nature, making it the third confirmed visitor to our solar system from beyond the gravitational influence of our Sun. Its trajectory, marked by a hyperbolic path, unmistakably declared its status as an outsider. However, never before had anyone on Earth detected a radio signal from an interstellar object. Not even in the entire history of radio astronomy, which had been in existence since the 1930s when Carl Jansky first detected radio waves emanating from the Milky Way, had such an occurrence been witnessed. Pause and reflect on this for a moment. We had just eavesdropped for the first time on the chemical voice of material that had been born around another star. Now, here lies the intriguing part. The coordinates of the sky where 3I-ATLAS was situated at the time of its discovery coincided perilously close to another renowned location, a region of space that had, 48 years earlier, given rise to the most enigmatic radio signal in the annals of the search for extraterrestrial intelligence. You might recognize it by its moniker, the WO signal. On August 15, 1977, the Big Air Radio Telescope in Ohio intercepted a narrowband signal of such intensity and precision that astronomer Jerry Emmons circled it on the printout and scribbled, "Wow," in the margins. The signal persisted for 72 seconds.
No researcher or institution claims that 3I-ATLAS is actively broadcasting a greeting or beaming us a cosmic encyclopedia. The signal detected is not a transmission in the conventional sense. Instead, it manifests as an absorption line, a specific fingerprint imprinted upon starlight by intervening material. This discovery stems from chemistry, the interaction of light with hydroxyl radicals, not from any act of communication. Nevertheless, the sheer structure of the observation, the remarkable precision of its detection, and the extraordinary improbability of capturing such a signal, particularly amplified by its eerie temporal and spatial echo of the WODO signal, has ignited a complex and persistent set of questions. These questions resist easy dismissal, forming a perfect storm of scientific curiosity that refuses to dissipate. This conundrum forces a profound inquiry. When the universe speaks, how can we discern whether its voice is born of natural processes or the intent of intelligence? How do we establish a reliable method to differentiate between the random noise generated by chemistry and physics and the deliberate, structured signal of something possessing the capacity to wish itself be heard? Perhaps this very line of questioning carries an inherent flaw. Maybe the chasm between nature and intelligence is not as absolute as we have traditionally imagined. Perhaps the boundary separating them is far more permeable, far blurrier than our current understanding allows. To grasp the full significance of detecting 3I-ATLAS at the precise moment Dr. Mia Kate observed those hydroxyl lines, one must appreciate the staggering improbability of the feat. At that critical instant, 3I-ATLAS was situated a mere 3.76 degrees from the Sun. To visualize this angular proximity, extend your arm fully and hold up your fist at that distance. Your fist spans approximately 10 degrees of the sky. Now extend your thumb. That subtends roughly 2 degrees. Imagine attempting to observe a specific feature located less than twice the width of your thumb held at arm's length, positioned perilously close to the most intensely bright object in the daytime sky. The challenge of such an observation is immense, underscoring the remarkable nature of the detection itself. The Sun, our solar system's central star, radiates across the entire electromagnetic spectrum. This intense flood of energy effectively drowns out other signals, creating an overwhelming blaze of radio noise that obscures the surrounding cosmos. For this reason, most sensitive radio telescopes deliberately avoid observing regions very near the Sun's blinding disk. The sheer power of the solar interference completely overwhelms the faint cosmic signals they seek to detect, making observation akin to trying to hear a single whisper at a deafening rock concert while standing perilously close to the main speakers.
Yet, in the precise calculations of astronomy, geometry reigns supreme. The remarkable proximity of the object 3I-ATLAS to the Sun presented not merely an observational obstacle, but also a unique opportunity. This near miss proved unexpectedly advantageous. 3I-ATLAS was streaking through the inner solar system at a distinct angle relative to Earth, neither racing directly towards us nor swiftly receding away.
This specific trajectory caused a crucial Doppler shift in the object's own emissions. The hydroxyl absorption lines characteristic of 3IATLAS were shifted away from the sun's dominant radio output, moving just far enough into a cleaner frequency band that even modest radio receivers could potentially discern them amidst the solar static. Securing this detection required pinpoint temporal accuracy. The observational window was incredibly narrow. Attempting the observation too early risked failure, as the object's volatile ices had not yet begun releasing significant material. Delaying the attempt until too late meant the object would swing completely behind the sun from Earth's viewpoint, vanishing entirely from our line of sight and becoming utterly unobservable. October 24th fell precisely within this critical sweet spot. It represented a fleeting interval where celestial mechanics, the activation of the object's chemistry, and the instrument's sensitivity converged perfectly, aligning the geometry, the chemical activity, and the instrument's capabilities with the strength of the emerging signal. Had observations with the mirror telescope occurred even 48 hours later, the chance for detection would likely have evaporated entirely. Now, let us delve into the significance of detecting hydroxyl radicals themselves. When water molecules within an object like 3IATLAS are struck by intense ultraviolet radiation emanating from a nearby star, they undergo a dramatic transformation. Far from evaporating quietly, these H2O molecules fracture violently under the stellar assault. The powerful UV photons shatter the water molecules, breaking them apart into their fundamental constituent parts. Vast numbers of hydrogen atoms surge away in one specific direction. Simultaneously, hydroxyl radicals, the O-containing molecules, remain suspended in their wake, appearing almost spectral, like lingering phantoms. This distinctive pattern represents one of the most basic and crucial chemical signatures associated with water throughout the cosmos. Remarkably, this identical chemistry underpins the conditions necessary for life as we know it on our own planet.
Every single molecule of water contained within the human body, constituting approximately 70% of its mass, possesses the inherent potential to decompose into these very same fundamental radicals, given the appropriate environmental circumstances. Consequently, when astronomers detect the specific absorption lines of hydroxyl in the vastness of space, they are directly observing the molecular fingerprints of H2O, the universal solvent, the essential liquid medium upon which terrestrial biology fundamentally depends. However, this particular observation was not a chance finding originating from a comet traversing the outer solar system or a distant stellar nursery within a nebula. Instead, the source was designated 3IATLAS, an object whose existence had stretched across millions or even billions of years as it drifted alone through the profound darkness between stars. Now, as this solitary traveler passed through the vicinity of our Sun, it began to release these volatile components trapped within its ancient structure. This event marked the first instance in human history where direct chemical data was obtained from material originating beyond our solar system. Crucially, this breakthrough was achieved not by deploying spacecraft to intercept dust grains, but by meticulously listening to the faint radio signals emitted as molecules within the drifting material broke apart in real time. Upon initially encountering the raw data, the scientists followed the inherent scientific protocol of skepticism. They methodically cross-referenced the detected signal against comprehensive databases cataloging potential sources of radio frequency interference. They investigated the possibility of nearby satellites contributing to the reading. They aligned the detection time with known sources of terrestrial noise for further comparison. Even after scrutinizing the initial finding, they reviewed records from 2 prior observation attempts conducted back in September to ensure consistency and rule out any prior anomalies. Both of these searches had come up fruitless. There was nothing. No signal, no hydroxyl, just silence. So why did it appear on October 24th? What had changed? The answer was intricately tied to timing. On September 20th and 28th, the comet remained distant from the Sun, still too cold for significant sublimation of water ice. The surface temperature was below the threshold where volatiles began to vaporize. However, by late October, everything had changed. The object was days away from perihelion, scheduled for October 29th, and the Sun's radiation was intensely hammering its surface. Ice that had remained frozen for eons finally warmed up, cracked, and released gas into the thin atmosphere surrounding the nucleus. With that gas came hydroxyl radicals. Billions upon billions of them, forming a cloud that absorbed radio light at exactly the frequencies that mere Kate was designed to detect.
The data integrity checks passed every test. The signal was real, and it was coming from exactly where 3IATLAS should have been based on its predicted path through space. But here's where the story takes another turn. 3IATLAS wasn't just behaving like a normal comet. As the object approached perihelion, researchers documented not 1, not 2, but 8 distinct anomalies in its behavior. Unusual tail dynamics, erratic brightness variations that didn't match standard models of dust production, off-axis jets firing in directions that seemed inconsistent with simple solar heating, and perhaps most strangely, the formation of both a tail and an anti-tail. The sight of Comet 3IATLAS defying celestial expectations left astronomers deeply intrigued. As it journeyed closer to the Sun, 2 distinct streams of dust emerged, flowing in diametrically opposed directions. This observation suggested a complexity far exceeding the familiar process of ordinary cometary outgassing. Typically, when a comet nears our star, the intense pressure exerted by sunlight and the stream of charged particles known as the solar wind forcefully ejects dust and gas away from the central nucleus. This relentless push invariably forms a single sweeping tail that points perpetually away from the Sun. Such a sun-avoiding trajectory has become one of the most dependable hallmarks of cometary nature. The anomaly presented by 3IATLAS, however, was profound. Observers identified what they termed an anti-tail, a secondary dust stream persistently pointing towards the very center of the solar system, directly towards the Sun itself. The symmetry of this dual-tailed structure was notably peculiar. The main tail and its solar-pointing counterpart displayed remarkably similar luminosity and extended over approximately the same distance, creating the striking illusion that the comet was expelling material simultaneously in 2 diametrically opposed directions. Further deepening the enigma were the observed jets emanating from the comet's surface. While jets are a common feature on active comets, expelling plumes of gas and dust through vents, 3IATLAS exhibited jets originating from locations that were not bathed in direct sunlight. This pointed strongly toward subsurface heating mechanisms actively triggering the outgassing.
It's entirely plausible that this assessment holds merit. The most straightforward interpretation suggests that 3IATLAS behaves much like any other comet discovered within our own celestial neighborhood, distinguished primarily by originating from a completely different stellar system during its formation. Nevertheless, the distinctive characteristics observed in its composition and behavior present puzzling anomalies that continue to occupy astronomers' thoughts late into the night, defying easy dismissal. To fully grasp the significance of this detection requires a broader perspective. 3IATLAS represents only the 3rd confirmed celestial body from interstellar space known to traverse our solar system's domain. The first such interloper, designated Oumuamua, made its unexpected arrival in the year 2017, instantly captivating and confounding the scientific community,
with its extraordinary acceleration patterns and the conspicuous absence of any visible atmospheric envelope or coma typical of comets. The second confirmed visitor, Borisov, graced our skies in 2019, displaying characteristics strikingly familiar, behaving remarkably like a standard comet without any perplexing deviations. Now, 3IATLAS has joined this exclusive group, seemingly occupying a middle ground, predominantly exhibiting commentary consistent with expected comet behavior, yet retaining sufficient unusual features to ensure the underlying mystery surrounding its nature persists. The very act of receiving detectable radio transmissions from this distant object marks a fundamental and transformative shift in the methodology employed by astronomers to study such interstellar travelers.
Prior to this breakthrough, the primary tools available consisted solely of optical telescopes for tracking their trajectories, spectrographs to analyze the specific wavelengths of reflected sunlight bouncing off their surfaces, and occasionally infrared measurements to gauge their temperature and composition. Radio signal detection was, quite frankly, considered highly improbable and rarely pursued. It simply wasn't seen as a viable avenue for investigation. However, the unprecedented sensitivity of the Meerkat telescope array, specifically tuned to listen in the L-band, a critical radio frequency range centered around 1.4 gigahertz, renders it uniquely qualified for this previously neglected form of astronomical observation. This sophisticated instrument comprises an array of 64 individual radio dishes strategically distributed across an expanse of 8 kilometers within the remote South African desert. These dishes function in precise concert, effectively combining their collecting power to create an aperture vastly exceeding the capabilities of any single telescope on Earth. Furthermore, this facility occupies one of the most radio-quiet sanctuaries on the planet, a location legally protected by stringent regulations designed to shield it from the pervasive electromagnetic interference that severely compromises the observational potential of telescopes situated in more densely populated regions. The trajectory of the interstellar visitor Oumuamua defies randomness. Its course aligns almost precisely with the ecliptic plane, the vast, flat disk that serves as the primary orbital stage for our solar system's planets. This specific alignment proves exceptionally uncommon. By fundamental definition, such interstellar objects originate from beyond the solar system's gravitational boundary, theoretically permitting arrival from any conceivable direction within the galaxy's three-dimensional expanse. Stars residing in the galactic halo, the spherical region surrounding the disk, typically journey towards the solar system at steep, dramatic inclinations, swooping down from above or rising sharply from below the familiar plane. Yet Oumuamua's approach was remarkably horizontal, tracing a path astonishingly similar to the planets themselves. This peculiar geometry has ignited significant debate. Some researchers cautiously speculate that this alignment might hint at a more local genesis, perhaps originating from the gravitational influence of a nearby star system whose own orbital plane happens to share a similar orientation with our own. Conversely, other scientists argue that such an alignment could simply be a matter of statistical chance, a rare but possible occurrence in the cosmic lottery.
Furthermore, a more profound and unsettling question lingers, unspoken yet unquestionably present. Could this very geometry, the flat, familiar plane of the solar system, itself be acting as an amplifier, subtly enhancing signals or phenomena that would otherwise remain entirely undetectable against the cosmic background? The South African Radio Astronomy Observatory captured the initial signal within hours of its passage. The data underwent rigorous scrutiny through their established verification protocols. This began with automated systems flagging potential sources of terrestrial or instrumental interference.
Subsequently, the observations underwent meticulous visual inspection by experienced astronomers. The signal was then cross-referenced against known astronomical sources and potential radio frequency interference databases. Additional consistency checks were performed across multiple frequency channels. Every single step yielded a clean result. The distinctive hydroxyl radical spectral lines manifested precisely where established physical theory predicted they should appear, displaying the correct Doppler shift corresponding to the object's motion, exhibiting the inspected line width, and demonstrating the appropriate relative intensities compared to other observed features. This sequence of confirmations unequivocally ruled out error or artifact. It was not a fleeting glitch. It was not a human mistake. The observations proved real, reproducible across the verification stages, and profoundly strange given the object's unexpected characteristics.
We have confirmed that ice solidified under the distant sun of an alien star and subsequently traversed light years of the universe's vast emptiness, retains its essential nature. It remains composed of water, and it continues to exhibit behavior indistinguishable from the ices that shape phenomena within our own solar system. This demonstration powerfully validates the fundamental principle that the laws of chemistry are universal constants. The very same molecules, the essential building blocks that make life conceivable here, exist abundantly out there. They drift silently through the galaxy, hitching rides on comets and asteroids, and who can speculate what other celestial travelers? This observation directly supports one of the central foundational assumptions of astrobiology, that the fundamental components necessary for life are not unique to Earth, reserved for our singular world. They are, in fact, widespread throughout the cosmos. The surface temperature of the interstellar object at the precise moment of its detection was calculated to be approximately 230 Kelvin. This temperature, cold by the standards of our planet, equating to minus 43 degrees Celsius, nevertheless provided conditions sufficiently warm for water ice located on its surface to transition directly from the solid state to a gaseous state, bypassing the liquid phase entirely, a process known as sublimation. These findings confirmed the expected behavior of a dirty snowball, a celestial body heated by solar radiation releasing its primordial ices. Further confirmation came from NASA's Swift Observatory, utilizing its ultraviolet telescope to observe Comet 3I/ATLAS in the critical weeks preceding its closest approach to the Sun. Swift's instruments unequivocally identified the telltale signatures of water molecules transitioning directly from solid to gas, sublimation, within the ultraviolet spectrum of the comet's coma. The observational evidence aligned perfectly. 3I/ATLAS exhibited the classic signatures of cometary activity, releasing gas at a rate entirely consistent with its measured size and its specific, relatively close, distance from the solar heat source. This behavior was entirely predictable for a comet entering the inner solar system. However, a profound anomaly remained. Unlike comets originating within our solar system, 3I/ATLAS did not form here. Its birthplace lay orbiting a distant, unidentified star, a system we will likely never observe directly. Now, this interstellar traveler was merely passing through our cosmic neighborhood on a unique, one-time journey. Its hyperbolic trajectory, shaped by the gravitational fields it encountered, would ultimately propel it back into the vast emptiness between the stars at an astonishing speed exceeding 40 kilometers per second. Yet, if 3I/ATLAS behaved solely as a conventional comet governed by well-understood physics, it would not have generated such intense scientific fascination. Some observers, analyzing tracking data with meticulous care,
have noted peculiarities in the object's orbital path. These deviations appeared too consistent, too precisely coordinated to be explained by the random jetting of gas and dust, the typical outgassing that slightly perturbs a comet's course. This unexpected regularity sparked speculation about the forces potentially acting upon this cosmic interloper. The enigmatic appearance of certain celestial bodies has led some to propose a startling explanation. Their distinctive tail and anti-tail configurations suggest the presence of controlled thrust mechanisms. This hypothesis centers on the observation of symmetrical jets ejecting material in precisely opposing directions. Such a configuration, theoretically, would enable minute and accurate adjustments to the object's flight path. Proponents of this idea argue that constructing an interstellar spacecraft while deliberately avoiding detection would necessitate a unique form of concealment. They suggest cloaking the vessel entirely within a mantle of cometary material, utilizing the sublimation process itself as the primary source of propulsion. Navigation would then be accomplished through the meticulous regulation of these gas jets.
From a considerable distance, such a craft would bear a striking resemblance to a natural comet. It is only through exceptionally detailed analysis of its trajectory, scrutinizing its movements with extreme precision, that the artificial origin might be uncovered. Let us be unequivocally clear, this entire proposition resides at the very edge of speculation, bordering on the realm of fantasy. However, it is not constructed entirely upon empty air. The underlying physics concerning the use of outgassing for propulsion has a solid foundation. Several proposals for interstellar probes have indeed envisioned this method. The concept involves coating a spacecraft with frozen hydrogen or water. Solar radiation would then induce sublimation of this icy layer. The expanding gas generated in this process would be channeled through nozzles to provide thrust. While this approach is significantly less efficient than conventional chemical rockets and yields relatively modest acceleration, its profound advantage lies in its simplicity. It requires no complex onboard power generation systems or vast stores of traditional fuel. Furthermore, it renders the spacecraft visually indistinguishable from a natural comet traversing the solar system. The observed deviations in trajectory, while real, fall well within the spectrum of possibilities produced by asymmetric outgassing in natural comets. Sophisticated thermal models simulating the volatile behavior of cometary material can adequately explain these observed path variations without needing to invoke advanced propulsion systems. And yet, the fundamental question persists, unresolved and intriguing. If such an object were truly artificial, how could we definitively confirm its origin? If an exceptionally advanced civilization desired to dispatch probes into the vastness of other star systems, and if they possess the intelligence to proceed with caution, those probes would inevitably need to mimic natural phenomena. They would strategically utilize gravity assists from planets and perform solar flybys. They would even potentially release chemicals in patterns that precisely replicate the complex and often unpredictable behavior of comets, thereby ensuring their presence remains undetected by casual observation. Here is the deeply rephrased and expanded narrative, adhering strictly to the original meaning and facts while significantly extending the length for enhanced flow and detail. The current sample size of confirmed interstellar objects traversing our cosmic neighborhood consists of merely 3 distinct entities. This profoundly limited dataset places us firmly at a distance from any meaningful ability to discern recurring patterns or signatures within their movements or behavior.
Achieving the statistical certainty necessary to differentiate between objects arriving naturally and the highly speculative possibility of artificial probes masquerading as comets or asteroids would require the detection of hundreds, even thousands, of such interstellar wanderers. Only then could astronomers begin to confidently separate genuine signals from mere statistical noise. Consequently, the hypothesis concerning deliberate maneuvering inherent to these objects remains, in principle, a conceivable scenario.
However, it currently stands unsupported by any tangible evidence gathered to date. Furthermore, such a hypothesis appears almost certainly unnecessary to account for the observed phenomena. That said, allow this contemplation to linger. What if occurrences perceived as coincidences are not truly random events? What if the universe, in its astonishingly vast complexity, occasionally generates arrangements or sequences that appear meticulously designed, even when they arise from entirely natural processes? And crucially, what if embedded within these intricate, seemingly patterned arrangements lies encoded information, a message yet to be deciphered by human intellect? Whether the object designated Oumuamua exhibits deliberate maneuvering or simply tumbles through the cosmos, governed solely by the fundamental impersonal laws of physics, its journey has culminated in an extraordinary encounter. Its path has brought it remarkably close to our solar system, placing it within observational reach. Its brightness proved sufficient to register clearly upon astronomical instruments. Timing aligned with uncanny precision, capturing its passage in a manner that produced a historic radio signature, an event permanently etched into the annals of scientific discovery. Is this convergence mere coincidence or the product of unseen choreography? The available data, regrettably, provides no definitive answer to this profound question, not at this juncture. Traditional approaches to the search for extraterrestrial intelligence, or SETI, have historically centered its efforts on a singular, focused objective, the detection of narrow-band beacons. The underlying rationale is both straightforward and compelling. Natural astrophysical phenomena, such as pulsars or masers, typically emit radiation spanning a broad swath of frequencies, creating a diffuse, noisy signal across the electromagnetic spectrum. In stark contrast, a deliberate transmission, deliberately crafted by an advanced intelligent civilization, would likely be engineered to be spectrally pure. Its energy would be concentrated into a single, highly specific frequency, the most efficient method for packing a coherent message into the limited power resources available for interstellar communication.
For decades, the central target of inquiry within this scientific field has been the relentless pursuit of specific electromagnetic emissions. This involves deploying massive radio telescopes, devices of immense scale, dedicating thousands upon thousands of observation hours to systematically scan the celestial vault. The objective? To detect extraordinarily narrow frequency bands exhibiting repeating patterns. Signals whose intricate modulation bears the unmistakable hallmarks of deliberate design and human-like intelligence. This dedicated quest commenced in 1960, a pioneering year when astronomer Frank Drake directed a radio antenna towards the proximity of Tau Ceti, a nearby sun-like star, and commenced a 6-month listening vigil. The outcome was profoundly silent. More than 65 years have since elapsed. Despite technological leaps in receiver sensitivity that would have appeared miraculous to Drake himself, the cosmic background remains deafeningly quiet. No repeating cosmic beacons flicker our way. No modulated transmissions deciphering alien encyclopedias arrive. Only the vast, persistent, and noisy silence of the universe. The recent detection of hydroxyl radicals within the atmospheric data gathered by the 360ATLAS facility compels a critical reevaluation of our entire approach to identifying extraterrestrial technological footprints. This discovery necessitates a fundamental paradigm shift in how scientists conceive of technosignatures, the potential markers of advanced alien technology. Could it be that humanity has been searching for the wrong kind of signal all along? Might intelligence, particularly of a highly advanced nature, not necessarily broadcast its existence intentionally seeking contact? What if the signatures left behind by sophisticated technology are instead subtle, easily overlooked markers woven seamlessly into the fabric of planetary chemistry or the subtle dance of celestial mechanics? These telltale signs, these technological imprints, could be entirely indistinguishable from the natural background processes of a world, detectable only if one possessed the precise knowledge and instruments to recognize them. This concept introduces the idea of non-intentional technosignatures. These are the inevitable byproducts, the accidental leaks of technological civilization operating on a grand scale. Industrial processes, energy generation, or megastructural engineering might produce detectable radiation or alterations to a world's environment, not because any entity wishes to announce its presence, but simply because advanced technology operating at planetary or stellar levels generates unavoidable side effects. Consider Earth as a tangible example. For over 100 years, our planet has been unintentionally broadcasting electromagnetic radiation into the void of space. Our television transmissions, radar installations scanning the skies, and satellite communications networks, all functioning as unintended cosmic lighthouses. This man-made electromagnetic noise propagates outward at the speed of light, gradually enveloping our home in an ever-expanding spherical bubble of human-generated interference. This bubble currently extends approximately 100 light-years in all directions from our solar system.
The same method employed by astronomers to identify the presence of hydroxyl radicals, OH, in interstellar space, specifically within the context of the 3IATLAS project, is precisely what is needed here. The array, uniquely positioned for this pioneering work, possesses the critical capability of simultaneously observing multiple frequency channels. It searches for distinct emission and absorption lines, the spectral fingerprints of complex organic molecules. These include water, carbon monoxide, formaldehyde, methanol, and all the other complex organic compounds known to appear in star-forming regions and, intriguingly, within interstellar comets. However, performing this observation demands meticulous care to filter out interference originating from terrestrial sources, such as radio transmissions or satellite signals. The array excels at this crucial task of environmental noise suppression. A key factor contributing to its success is its location within the Karoo region. This area is renowned for being one of the most radio-quiet places on Earth, a status actively protected by specific South African legislation designed to prevent radio frequency pollution. The successful detection of hydroxyl radicals in the 3IATLAS dataset stands as concrete evidence. It passed every stringent interference check imposed by scientists, demonstrating the array's exceptional suitability for this delicate form of astronomical observation. The celestial signal manifested solely when the observatory's sensitive instruments were precisely aligned with the comet's predicted celestial coordinates. As the comet traversed a darkened vault of night, the signal remained locked on to its trajectory, demonstrating an uncanny correlation with the object's own motion across the sky. Furthermore, its frequency underwent a precise Doppler shift, a subtle stretching or compression of its waves, matching the exact magnitude calculated from the comet's measured velocity. This was unequivocally not an electronic artifact or atmospheric interference. It was a genuine astronomical phenomenon. Scientists are actively pursuing further verification, seeking to replicate this detection using other major radio observatories. The massive Green Bank Telescope in West Virginia, the 500-meter Aperture Spherical Telescope in China, and the extensive Very Large Array in New Mexico all possess the sensitivity to potentially detect similar hydroxyl radical, OH, spectral lines emanating from celestial bodies like comets, provided the geometric alignment between the telescope, the comet, and Earth is favorable. However, a significant complication arises, noted as the third variable in the observations. Earlier attempts to detect a signal during previous comet passes yielded nothing. This critical detail reveals the signal's fleeting, transient nature. It manifests only under a specific, unobserved set of conditions.
Without continuous, dedicated monitoring of such objects,
It remains impossible to determine what precise trigger initiates the release of this signal. This uncertainty, in turn, compels researchers to confront a profound and unsettling question that lies at the very heart of SETI philosophy. What if an extraterrestrial technological signature perfectly mimics the subtle patterns of natural chemistry? How could humanity possibly discern between a purely natural molecular emission and an artificial one designed to resemble it? Imagine an advanced civilization possessing mastery of molecular-scale engineering, capable of constructing machines operating at the nanometer level. Such beings could potentially orchestrate chemical reactions with atomic precision, synthesizing complex molecules or releasing them in meticulously controlled sequences. They could engineer spectral signatures, unique fingerprints of light absorption or emission, that appear entirely natural and commonplace to conventional analysis. Yet, within these seemingly ordinary patterns, they might embed encoded information through intricate variations, the specific ratios of different atomic isotopes, the precise timing of molecular release events, or complex correlations between different molecular species detected simultaneously. Unless scientists possessed an exhaustive reference library cataloging the full spectrum of possible natural cosmic spectra, and developed algorithms of extraordinary sophistication capable of detecting minute statistical anomalies within these patterns, such a deliberate, artificial signal would remain utterly indistinguishable from the background hum of the universe. The signal, potentially originating from an advanced civilization, could well be cleverly concealed within the very fabric of ordinary chemistry, existing right before our eyes, yet remaining undetected. This fundamental challenge defines the contemporary struggle in identifying technosignatures during the 21st century. While humanity has achieved remarkable progress in developing instruments of extraordinary sensitivity, capable of discerning the faintest traces of individual molecules adrift on comets located millions upon millions of kilometers away, our intellectual capacity to truly interpret these complex detections has not kept pace. The critical gap lies not in our ability to perceive subtle signals, but rather in our skill to differentiate between the profound complexity inherent in natural phenomena and the specific patterns indicative of deliberate engineering. Consequently, a paradigm shift is imperative. We must abandon the simplistic notion that the search for extraterrestrial intelligence constitutes a binary outcome. Either a clear beacon is found, or nothing is detected at all. Instead, we need to conceptualize this endeavor as a continuous spectrum, a gradual gradient of signals. This spectrum ranges from those that are unmistakably natural and explainable by well-established physical and chemical laws, through an intermediate zone characterized by ambiguous structures that defy easy categorization, all the way to signals that are demonstrably artificial and engineered. The intriguing phenomenon known as the 3IATLAS faults occupies a position firmly within this ambiguous middle ground. It possesses characteristics that are natural enough to potentially be explained by standard physics and chemistry, yet simultaneously exhibits enough unusual features to genuinely provoke profound questions and sustained curiosity. To grasp the full significance of this challenge, we are compelled to retreat momentarily and confront the underlying philosophical question that permeates this entire field of inquiry. What if the boundaries separating the natural world from intelligence are far more porous and less distinct than our historical frameworks have permitted us to believe? For centuries, human thought has diligently constructed a conceptual barrier, erecting a rigid distinction between natural processes governed solely by the immutable laws of physics and chemistry
and those phenomena arising from conscious intent and intelligent design. This division has become deeply ingrained in our scientific understanding. However, perhaps this perceived separation is nothing more than an illusion, a product of our inherently limited perspective and cognitive constraints. Perhaps intelligence is not an entirely separate entity operating outside nature's domain. Instead, it might be an emergent property, a specific manifestation arising directly from nature itself. It could represent one particular expression of the universe's fundamental tendency to organize matter and energy into ever more intricate and complex structures, a process unfolding according to the same underlying principles that govern the cosmos. In this view, intelligence becomes a natural, if rare, consequence of the universe's drive towards increasing complexity, blurring the lines we once considered absolute. Therefore, if this principle holds true, the crucial distinction separating a natural comet from a speculative artificial probe becomes significantly blurred. Both phenomena, ultimately, represent manifestations governed by identical fundamental physical laws. The detection of hydroxyl radicals originating from 3 distinct comets, an occurrence almost certainly natural, provides compelling evidence. What we observe is tangible proof that interstellar ices possess the capacity to transport the essential chemical constituents of life across vast expanses of light-years of seemingly empty space. Consider water itself, the universal solvent, the molecule indispensable for the existence of Earth's oceans, your own blood, and every living cell upon this planet. Its presence in plentiful quantities on objects formed within other star systems speaks volumes.
These complex molecules begin their journey by freezing onto minuscule dust grains within the swirling environments of protoplanetary disks. As planets coalesce from these disks, the ices become incorporated into the developing comets and asteroids. Subsequently, gravitational interactions, perhaps involving the tug of giant planets, can eject these icy bodies from their birth systems, propelling them into the cold depths of interstellar space. Once cast out, these frozen wanderers embark on enduring journeys, drifting for periods ranging from millions to billions of years. During this time, they endure exposure to cosmic rays and the faint glow of starlight, yet remain sufficiently cold to preserve their volatile contents, the water and complex organic molecules, locked within their frigid sanctuaries. Should one of these ancient comets or asteroids bearing this primordial cargo encounter another star system, gravitational forces may draw it inward. As the object approaches the new star, it begins to warm. This heating triggers the release of its frozen volatiles. Consequently, the comet delivers its precious payload, water and organic compounds, to any planets or worlds existing within that distant system. This process embodies panspermia in its most scientifically defensible form. It does not advocate the radical proposition that fully formed living organisms traverse the stars themselves. Instead, it presents the conservative but powerful claim that the fundamental chemistry upon which life depends can, indeed, make this interstellar voyage. Life, after all, necessitates certain prerequisites: a source of liquid water, organic molecules, and energy sources. Comets, as celestial couriers, offer a plausible mechanism for delivering both the essential liquid water and the organic compounds to nascent or barren worlds, potentially seeding them with the chemical groundwork for life. The third essential ingredient for life, as we understand it, exists on any planet situated within a star's habitable zone, where temperatures allow liquid water to persist upon its surface. When these 3 critical factors, the presence of water, essential organic compounds, and a usable energy source,
converge within an environment that provides stability over immense timescales. Biological processes may initiate spontaneously. This emergence wouldn't necessarily be the result of some external agency bestowing life, but rather a natural consequence. Chemistry, granted sufficient time and the appropriate planetary setting, inherently progresses towards increasing complexity. Amino acids, the fundamental building blocks of proteins, can form spontaneously under specific prebiotic conditions. Lipid molecules readily organize themselves into protective membranes. Remarkably, certain RNA sequences have the capacity to catalyze their own replication, acting as both blueprint and machinery.
Consequently, life might not represent a singular cosmic miracle, but rather an inevitable outcome, a predictable consequence of chemical principles unfolding on planetary surfaces where the conditions are met. However, if this perspective holds true, why does the galaxy appear overwhelmingly silent? This profound silence constitutes the famous Fermi paradox, the striking contrast between the high probability of extraterrestrial civilizations existing, derived from the staggering multitude of stars and planets throughout the cosmos, and the complete and utter absence of any detectable evidence for their presence. If the fundamental components for life are widespread and chemistry demonstrably leads towards complexity, one would anticipate biological emergence occurring on countless worlds across the universe. Furthermore, if biology proves common, the development of intelligence should occur sporadically, perhaps infrequently, but considering the sheer number of stars within our own Milky Way galaxy, hundreds of billions, even an exceedingly small fraction would likely produce millions, perhaps even billions of technological civilizations scattered throughout the galactic disk. Yet, the critical question remains, where are they? Why have we not observed their radio transmissions, glimpsed their colossal megastructures, or encountered probes dispatched to explore the vast interstellar expanse? Perhaps the resolution to this enigma is fundamentally simpler than our most elaborate theories propose. Maybe intelligence, while not uncommon, arises far less frequently than we might hope. Equally plausible, and potentially more significant, is the notion that communication across the immense gulfs separating star systems presents a challenge so formidable, demanding such colossal resources and energy expenditure, that the vast majority of civilizations simply find the endeavor impractical or elect not to engage, leaving the galaxy resoundingly quiet. Perhaps they exist somewhere out there, dwelling upon their own worlds, cultivating civilizations of their own design. Yet they remain silent, broadcasting nothing observable, for reasons beyond our current comprehension, or perhaps simply because no compelling motive exists to do so. Another perspective suggests intelligence might be a widespread phenomenon across the cosmos, yet inevitably ephemeral. Civilizations could arise and flourish only to fade away within astronomical timeframes measured in mere thousands of years, fleeting instants in the universe's grand chronicle, rarely intersecting with one another's brief existences. Or, critically, perhaps our methods are fundamentally flawed. We scour the void for the unmistakable beacon of radio transmissions, yet the true signatures of life might be concealed within the intricate dance of chemistry itself, or encoded within orbital mechanics phenomena that remain unnamed, untheorized, and beyond our present understanding.
Or, and this notion profoundly unsettles those who dedicate their lives to searching for life beyond Earth, perhaps Earth occupies a singular position. Perhaps the fundamental chemical processes leading to life are relatively common, but the crucial initiating spark, the transition from non-living matter to the complexity of biology, is extraordinarily rare. Maybe the emergence of life demands not merely the presence of suitable raw materials, but a highly improbable sequence of fortuitous events. The perfect planet must reside at precisely the right distance from a nurturing star, It must be accompanied by a substantial moon, acting as a cosmic stabilizer for its rotational axis. It requires active plate tectonics, functioning as a planetary engine to recycle vital carbon compounds. It necessitates a powerful magnetic field, a protective shield guarding its surface from lethal stellar and cosmic radiation. Furthermore, it ideally possesses a colossal gas giant situated in its distant outer reaches, acting as a cosmic sweeper to deflect devastating cometary and asteroidal impacts from the inner, life-hosting region. When one assembles enough such necessary conditions, each individually plausible, yet collectively forming an exceptionally improbable configuration, the result is a formidable filter. This filter offers a potential explanation for why life, as we know it, exists abundantly here within our own solar system, yet remains undetected in the vast expanse of the observable universe beyond. Returning to the subject of exoplanets and the lessons they impart, the detection of hydrocarbons within the atmosphere of an alien world, regardless of whether their origin proves natural or, hypothetically, artificial, serves as irrefutable proof. It demonstrates that we now possess the capability to analyze the very chemical composition of materials existing light years away, utilizing the technique of spectroscopy. This achievement represents nothing short of a revolution in the field of planetary science, fundamentally expanding our reach and understanding of worlds orbiting other stars.
Prior to this moment, our understanding of celestial bodies beyond the boundaries of our solar system was derived solely from indirect approaches. Astronomers relied on transit spectroscopy to probe the atmospheres of distant exoplanets, infrared observations to analyze dust-laden disks, and computer simulations that extrapolated from local knowledge. However, the arrival of 3IATLAS provided us with a sample, albeit not physically, but sufficiently close that our instruments could perform real-time analysis of its volatiles. This marked a significant advancement, allowing for direct sampling without the need for a spacecraft. The James Webb Space Telescope is transforming the field of exoplanet science by mapping atmospheric compositions with extraordinary precision. In November 2025, it observed the ultra-hot Jupiter known as ESPO 18b, producing a comprehensive three-dimensional temperature map of the planet's atmosphere. This gas giant, with a mass approximately 10 times that of Jupiter, orbits its star with such proximity that its year lasts less than a day. The dayside temperature surpasses 2,500 Kelvin, a heat intense enough to vaporize most metals. By monitoring the planet's infrared brightness as it orbited, the telescope was able to reconstruct the temperature distribution across various altitudes and longitudes. Different molecules, such as carbon monoxide and water vapor, were concentrated in specific regions, while titanium oxide formed clouds at certain altitudes. The underlying physics remains consistent with what we used to study 3IATLAS, albeit applied on a different scale. In both cases, scientists utilize the principle that molecules absorb and emit light at characteristic frequencies determined by quantum mechanics. These frequencies serve as unique fingerprints for each species, enabling their identification without direct physical interaction. This method allows for the remote analysis of celestial bodies, providing invaluable insights into their composition and behavior.
Here is the deeply reworked narrative, expanding upon the original concepts while strictly adhering to its meaning and facts, with all numbers written out and promotional language removed. This meticulous process of light analysis applies universally, whether the target lies astonishingly close at 100 million kilometers away, a comet streaking through our own solar system, or resides profoundly distant, hundreds of light years beyond. The fundamental methodology remains consistently powerful across these vast scales. Astronomers begin by meticulously gathering photons, then employ specialized instruments to disperse this collected light, separating it into its constituent wavelengths, like a prism revealing hidden colors. Within this resulting spectrum, they search for distinct absorption or emission features, specific signatures where light has been diminished or amplified at precise points. By comparing these unique spectral fingerprints against extensive databases cataloging known molecular transitions, astronomers can definitively identify the specific atoms and molecules present in the target's atmosphere or material. Furthermore, the precise characteristics of these features allow scientists to infer the intricate physical conditions, such as temperature, pressure, and density, necessary to produce them. This technique constitutes one of astronomy's most formidable investigative tools. Significant advancements in detector technology and the ability to resolve fine spectral details have dramatically revolutionized this method. It has evolved remarkably from serving as a relatively crude diagnostic instrument into a highly precise probe capable of examining the environments of objects situated at extreme distances. Consider the remarkable progress in studying exoplanets, planets orbiting stars outside our solar system. Just 50 years ago, the very detection of such distant worlds appeared utterly impossible. Then, 20 years ago, astronomers achieved the capability to measure fundamental planetary parameters like mass and the period of their orbits, yet possessed no direct knowledge regarding their atmospheric compositions. 10 years prior to the present era, the advent of transmission spectroscopy finally revealed the presence of water vapor and other specific molecules within these alien atmospheres, marking a pivotal breakthrough. Currently, with the advanced capabilities of the James Webb Space Telescope, researchers are now actively mapping complex three-dimensional atmospheric structures, tracking dynamic weather patterns, and identifying distinct chemical gradients across these distant worlds. This progression has followed an exponential trajectory, accelerating rapidly with each technological leap. If this accelerating rate of advancement continues, and if humanity constructs even more monumental telescopes during the coming decades, the potential becomes truly transformative.
Such future instruments will eventually enable the direct imaging of exoplanets, resolving their surfaces into discernible detail. This will allow for the systematic search for biosignatures, chemical indicators suggestive of life, and may even extend to the detection of artificial lights or atmospheric pollution signatures created by advanced industrial civilizations. The most profoundly transformative moment in this ongoing exploration, however, is anticipated to occur very soon. In the latter part of the year 2025, the Vera C. Rubin Observatory in Chile is poised to conclude its final commissioning tests, preparing to initiate its comprehensive scientific mission. Imagine the moment the Rubin Observatory inaugurates its official survey of space and the vast expanse of time. This singular event will propel astronomy across an unprecedented threshold, marking a point of no return for our understanding of the cosmos. The sheer scale and capability of this new facility promise a transformation so profound that it dwarfs all previous achievements in celestial discovery. Within its very first year of operation, Rubin is projected to uncover more solar system objects than humanity managed to identify throughout all preceding centuries combined. The magnitude of this anticipated finding is truly staggering. This remarkable capability stems directly from Rubin's formidable technical prowess. Its 8.4-meter primary mirror, coupled with the largest digital camera ever constructed for astronomical purposes, grants it an unparalleled view. This combination allows the observatory to meticulously image the entire visible sky every few nights. Over a decade of operation, this relentless scanning will yield an unprecedented time-lapse chronicle of the universe itself, spanning 10 years of cosmic activity. The systematic nature of this survey ensures nothing slips through the cracks. Every single celestial body that exhibits motion against the static background of distant stars will be automatically detected, meticulously tracked, and comprehensively cataloged. Current projections indicate the discovery of 5 million new asteroids residing within the main belt between Mars and Jupiter. Additionally, hundreds of thousands of objects originating from the distant Kuiper belt lying far beyond the orbit of Neptune are expected to be revealed. Furthermore, dozens of interstellar travelers, objects originating from beyond our solar system, will be identified during its operational lifetime. It is important to note that this final estimate is considered conservative. The reason for this cautious optimism lies in the limitations of previous observational efforts.
In the 8 years since humanity first detected an interstellar object using surveys that only covered small, fragmented portions of the sky, just 3 such visitors have been found. Rubin's comprehensive approach eliminates these blind spots. It possesses the power to catch objects that prior instruments inevitably missed, bodies that were simply too faint, moving too swiftly, or located in celestial regions overlooked by earlier, more limited surveys. The discovery of 3IATLAS in July of the year 2025, just a few short months before its October passage closest to the Sun, serves as a poignant illustration of this limitation. This late detection severely constrained researchers' ability to coordinate vital observations, request precious telescope time, and meticulously plan dedicated study campaigns. Had Rubin Observatory been actively surveying at that time, it is highly probable that 3IATLAS would have been detected significantly earlier. It might have been identified while still residing in the outer reaches of the solar system, appearing faint but clearly discernible against the backdrop of distant stars.
If an object exhibits movement faster than predicted by standard models, if its trajectory reveals a hyperbolic path, indicating it likely originated beyond the solar system, or if its spectral characteristics fail to align with any known class of asteroids or comets, the system automatically flags it for further investigation. Within mere hours of this initial detection, such anomalous objects are brought definitively to the attention of professional astronomers. These specialists can then seamlessly request additional, more detailed observations using specialized telescopes or alert other relevant facilities worldwide to focus their instruments. This rapid response mechanism is precisely what will ensure that the next significant interstellar visitor, such as a phenomenon akin to the 3IATLAS, is caught before it becomes another fleeting event, lost to science due to delayed recognition. A century ago, the detection of a new asteroid represented a major scientific milestone, a noteworthy achievement worthy of publication and celebration within the astronomical community. Today, the landscape has transformed dramatically. Advanced automated surveys now discover hundreds, even potentially thousands of such celestial bodies nightly. Looking forward a decade, the scientific community anticipates a profound shift. Interstellar objects will transition from being rare, once-per-decade sensations that captivated global attention to becoming routine occurrences. They will be regularly identified, systematically cataloged, and diligently studied as an integral part of the ongoing, relentless survey efforts. This anticipated normalization of interstellar object discoveries is simultaneously a source of immense excitement for the new scientific frontiers it opens, and a sobering reminder of humanity's evolving capacity to observe and understand the vast, dynamic cosmos beyond our own solar system. The anticipation is palpable as the prospect of rapid data accumulation looms, enabling us to address statistical inquiries with increasing confidence. How frequently do interstellar visitors grace our solar system? What can we discern about their sizes and compositions?
Do they predominantly cluster near the ecliptic plane, or are their origins more diverse, arriving from random directions? This prospect, while exciting, carries a sobering weight. Each discovery will transition from a unique marvel to a singular data point within a broader statistical framework. Consider the implications if 3IATLAS was not an anomaly, but merely the first to make contact. Perhaps interstellar objects traverse our cosmic neighborhood with regularity, passing through at a rate of tens or even hundreds annually, undetected due to their faintness and swiftness. The advent of Rubin, an observatory poised to unveil these celestial wanderers, promises a transformative era. When we begin to witness dozens of such objects annually, rather than the sporadic appearance of one every few years, the realization will dawn upon us. The galaxy is a web of interconnected systems, far more so than previously imagined. The exchange of material between planetary systems is an ongoing process. Comets, cast out by gravitational forces, become the comings and goings of another system. The galaxy, thus, is not a mere assembly of isolated islands, but a dynamic network, where the flow of mass between stellar neighborhoods is richer and more frequent than ever conceived. Every planetary system acts as both a donor and recipient, contributing to this cosmic ballet of ejection and capture. Throughout the year 2025, pulsar timing arrays, networks of radio telescopes meticulously monitoring the rhythmic pulses of dozens of millisecond pulsars scattered across the galaxy, have reported anomalies. These cosmic clocks, spinning hundreds of times per second and beaming radio pulses towards Earth with unparalleled precision, exhibit a slight irregularity, defying the expected regularity. Minute deviations, seemingly insignificant in isolation, reveal a profound cosmic dance when observed over extended periods. These variations, though infinitesimal in scale, demonstrate undeniable statistical significance across months of meticulous astronomical monitoring. Most compellingly, they exhibit clear correlation. When the precise rotational rhythm of one neutron star pulsar shifts, others across the celestial sphere follow suit in a remarkably synchronized pattern. This intricate synchronization points to a fundamental force at work, a pervasive stretching and compressing effect acting upon the vast interstellar distances separating our solar system from these distant cosmic lighthouses. These celestial phenomena are the remnants of colossal stellar giants that met their end in cataclysmic supernova explosions. What remains is the incredibly dense core, a neutron star whose matter defies terrestrial comprehension. A mere teaspoon of its material would possess a mass exceeding that of the mighty Mount Everest. Such objects spin with astonishing regularity, often completing hundreds or even thousands of rotations within a single second. Their magnetic fields are among the most powerful known in the universe, so intense that they act as colossal particle accelerators, funneling energetic radiation into focused beams. As these beams sweep across the cosmos like the rotating beacon of a lighthouse, they present a pulse of detectable energy to Earth-based observatories each time the beam aligns with our line of sight. This extraordinary rotational stability earns them the title of nature's most precise clocks, some exhibiting stability surpassing even the most sophisticated atomic timekeeping devices constructed on our planet. Astronomers leverage this natural precision through instruments known as pulsar timing arrays. These sophisticated networks continuously monitor the arrival times of pulses from multiple neutron stars distributed throughout the galactic neighborhood. The principle is rooted in Einstein's groundbreaking theory of general relativity, which predicts the existence of gravitational waves, ripples in the very fabric of space-time itself. When such a wave traverses our galaxy, it doesn't merely pass through, it actively distorts space. It stretches distances in one spatial direction while simultaneously compressing them in the perpendicular direction. This distortion subtly alters the effective distance between Earth and each pulsar. If the space-time along the line of sight is momentarily stretched, the pulse's journey to us takes slightly longer than anticipated, causing it to arrive late. Conversely, if space-time is compressed along that path, the pulse reaches us slightly early. The timing arrays are sensitive enough to detect these minuscule discrepancies in pulse arrival times. And this is precisely what these arrays have been registering over recent years. They detect a persistent, low-frequency signal characterized by a distinct correlation, a signature imprinted by gravitational waves oscillating at ultra-low frequencies. These waves have periods measured in years, even decades, representing a frequency range vastly different from the much higher frequency, millisecond-scale gravitational waves detected by terrestrial observatories like LIGO and Virgo, which rely on laser interferometry to sense distortions caused by much more energetic, nearby cosmic events such as black hole mergers. The prevailing explanation centers on binary systems comprising supermassive black holes. These extraordinary cosmic objects, each possessing a mass millions or even billions times greater than our own Sun, reside at the hearts of far-flung galaxies. As these titanic pairs dance towards their inevitable collision, they set the very fabric of space-time into motion. Imagine them stirring the cosmic medium with the gentle persistence of spoons swirling through viscous honey. This profound interaction generates ripples, gravitational waves, which then propagate relentlessly outward across the universe at the ultimate cosmic speed limit, the speed of light itself. However, the narrative takes a fascinatingly speculative turn at this juncture. Certain theoretical physicists propose that the observed signal might not originate solely, or even primarily, from the gravitational waves produced by these colossal black hole mergers. They suggest an alternative, more enigmatic possibility: dark matter. Not the familiar, cold, non-interacting particles favored by most standard cosmological models, but rather something fundamentally more exotic and elusive. This could involve oscillating fields, subtle quantum fluctuations inherent to space-time itself, or perhaps even topological defects, remnants sculptured during the universe's tumultuous infancy, frozen in the cosmic ice. Dark matter undeniably dominates the mass budget of the galaxy, outweighing the familiar stars, gas, and dust by a factor of 5 to 1. Yet, despite its overwhelming gravitational presence, it remains stubbornly invisible to direct detection. Every sophisticated experiment, constructed with the specific aim of capturing a dark matter particle on camera, has yielded nothing but silence, a profound cosmic puzzle. This persistent absence of evidence has led some to reconsider the very nature of dark matter. Perhaps, they theorize, it isn't composed of discrete particles at all. Maybe, instead, it manifests as waves, fluctuations within some profound, as yet unmisunderstood cosmic field. And crucially, these fluctuations might interact with the geometry of space-time itself in ways that produce signals indistinguishable from gravitational waves within our current detection capabilities. This speculative connection resonates metaphorically with the notion that the cosmos pulses with an inherent rhythm, that beneath the apparent chaos, a fundamental cadence underpins reality itself. Stars spin, planets orbit, gravitational waves oscillate through the void, and even the grand expansion of the universe accelerates and decelerates depending on the delicate cosmic balance between matter and dark energy. Indeed, it seems almost everything within the vast expanse of the cosmos follows recognizable cycles and repeating patterns, manifestations of the deep, underlying physics governing existence. Perhaps these patterns constitute a form of communication, not intentional, but informative, broadcasting the structure of reality to anyone capable of measuring them. Highlight the parallels. Both pulsar timing and hydroxyl absorption rely on precise frequency analysis. In pulsar timing, one measures the frequency of radio pulses, tracking nanosecond variations over months. In spectroscopy, one measures the frequency of light absorbed or emitted by molecules, identifying chemical species from sub-megahertz line widths. Both techniques push measurement precision to absurd limits, extracting information from signals so faint they are barely above noise. And both reveal phenomena that would be invisible without those precise measurements. Gravitational waves in one case, molecular abundances in the other. Now, speculate. Could interstellar objects be responding to galactic-scale rhythms? If gravitational waves from black hole binaries are constantly washing through the galaxy, could they interact with matter in subtle ways, perhaps altering orbital dynamics or triggering outgassing events on comets? The forces involved are unimaginably weak, far too small to measurably affect a macroscopic object.
But over millions of years, across billions of objects, could cumulative effects add up to something observable? It's wildly speculative, bordering on fringe science. But it's the kind of question that sometimes leads to genuine insights, because the universe is interconnected in ways we don't fully understand. The boundaries separating seemingly unrelated cosmic events from subtle, underlying causes often proves far more delicate than conventional perception allows. While astrophysicists still lack a definitive explanation for the puzzling pulsar timing anomalies detected over recent years, these enigmatic signals are already reshaping fundamental astrophysical understanding. Should these waves originate from gravitational ripples generated by merging supermassive black holes, it would constitute a profound validation of long-standing theoretical predictions concerning such cataclysmic cosmic collisions. This confirmation would further solidify the extraordinary robustness of Einstein's theory of general relativity under the most extreme gravitational conditions imaginable. Conversely, if the signals stem from an entirely novel source, perhaps elusive dark matter interactions or previously unrecognized physical phenomena, the implications would be revolutionary. Such a discovery would signal humanity's imminent arrival at a pivotal scientific paradigm shift, potentially overturning core tenets of modern cosmology and fundamentally altering our comprehension of universal structure and behavior. Crucially, irrespective of the ultimate explanation, the astronomical data itself is indisputable. The detected correlations demonstrate statistical significance beyond reasonable doubt, and the phenomenon driving these signals operates on cosmic scales and within gravitational regimes that utterly dwarf the familiar forces and distances governing our terrestrial existence. October 2025 marked another significant milestone in observational astronomy. The European Southern Observatory's flagship instrument, the 4-meter multi-object spectroscopic telescope, abbreviated as FOST, successfully concluded its rigorous commissioning phase and commenced full-scale scientific operations. The very name FOST underscores the instrument's primary function. It transcends the simple role of a telescope. Instead, FOST is a dedicated spectroscopic surveying machine, uniquely capable of simultaneously observing 2,000 separate celestial objects. Its advanced technology meticulously captures spectra from each target, enabling the analysis of light composition and motion. Over its anticipated operational lifetime, the instrument is poised to process and analyze millions of individual astronomical targets, generating an unprecedented volume of spectroscopic data. This capability makes FOST the indispensable tool for ambitious projects requiring stellar-scale chemical mapping.
For those aspiring to construct a detailed chemical atlas charting the intricate composition of our own Milky Way galaxy, FOST offers the necessary precision. It is equally vital for the comprehensive classification and monitoring of every comet and asteroid traversing the inner regions of our solar system. Furthermore, FOST is the essential instrument for unraveling the mysteries of galactic evolution. By measuring the chemical composition of millions of individual stars across vast stretches of space and time, astronomers can piece together the intricate history and developmental processes that have shaped the galaxy we inhabit. The underlying technology driving this powerful instrument is elegantly straightforward yet profoundly effective, designed specifically for high-throughput, large-scale spectroscopic surveying. A 4-meter primary mirror acts as the celestial eye, gathering faint photons streaming from distant stars and solar system bodies. Within this sophisticated structure, an intricate array of robotic fiber positioners operates with remarkable precision. Each slender fiber, roughly the diameter of a human hair, functions as a light conduit, capable of being swiveled and placed anywhere within the telescope's expansive field of view. Once positioned, these fibers channel the collected starlight or reflected sunlight from specific astronomical targets directly into powerful spectrographs. The resulting spectra, meticulously recorded by these instruments, serve as cosmic fingerprints. They reveal a treasure trove of physical information encoded within the light itself: the intricate chemical composition of the object, its precise temperature, its velocity relative to Earth, and numerous other fundamental properties. This spectroscopic analysis transforms seemingly intangible starlight into concrete data about the nature of the observed phenomena, whether it be a distant star, a comet hurtling through space, or a small, dark asteroid. The true operational revolution, however, lies in the system's automation. Unlike traditional telescopes requiring constant human direction, this facility can autonomously move from one target to the next. It operates throughout the night, systematically covering vast swaths of the celestial sphere without pause or error. This relentless, efficient scanning capability promises an unprecedented census of the night sky. The primary scientific goals for this immense data set are particularly focused on our own cosmic neighborhood. The collected spectra will play a vital role in classifying the myriad small bodies populating the solar system. Astronomers will use the detailed chemical signatures to distinguish between different asteroid taxonomies, separating them into their distinct compositional groups. It offers the potential to identify comets that have been masquerading as asteroids by their appearance alone, revealing their icy, volatile-rich true nature.
Crucially, the system could catch interstellar visitors, objects originating from beyond our solar system, before they reach their closest approach to the Sun, perihelion, providing an invaluable early warning. Consider the scenario involving an object like 3IATLAS. Had this interstellar visitor returned on a different trajectory, passing through the designated survey footprint, the telescope would have automatically captured its spectrum. Within mere hours of the initial detection, the unique velocity profile and chemical composition gleaned from the spectrum would have flagged the object as likely interstellar, triggering immediate scientific attention. This connects directly to the imperative of early interstellar detection. Future generations of these next-generation instruments, boasting even wider fields of view and faster survey capabilities, could potentially spot such objects significantly earlier as they traverse the outer reaches of the solar system. This extended warning period would grant precious time for critical follow-up observations by other observatories around the globe and beyond. The detection of hydroxyl OH radicals by the Murchison Wide Field Array, MIA-KATE, in 3IATLAS occurred during a fleeting, narrow window. This window existed only when the specific geometric alignment of the comet with Earth and the chemical processes releasing volatiles coincided perfectly. However, if optical surveys had identified 3IATLAS months earlier, while it was still residing in the distant, cold regions of the outer solar system, radio astronomers would have possessed foreknowledge. They could then have planned their observations in advance, meticulously tracking the very onset of volatile release as the comet began its inward journey towards the Sun. This proactive approach would have allowed them to measure precisely how the production of hydroxyl increased and evolved in response to the comet's proximity to solar radiation.
This expansion enriches the original text by elaborating on the telescope's function, the significance of spectroscopy, the operational advantages of automation, the specific scientific objectives for small body classification, the critical importance of early detection for interstellar objects, and the potential scientific gains from earlier identification and coordinated follow-up, all while strictly adhering to the facts presented in the source material and expanding the narrative flow. The scientific exploration of interstellar objects has undergone a revolutionary transformation, shifting from sporadic, opportunistic observations to meticulously planned, systematic campaigns. This paradigm shift, crucial for understanding our cosmic neighbors, hinges on instruments like the Formosa network and the rapid response capabilities of facilities across Europe and South Africa. When an optical telescope such as Formosa detects an anomalous celestial object, it instantly triggers automated alerts.
These signals are disseminated to a global constellation of observatories, including radio telescopes operated by institutions like MIT, powerful infrared telescopes such as the Very Large Telescope, and space-based platforms like the James Webb Space Telescope. Within mere hours, this coordinated effort allows multiple instruments, operating across vastly different wavelengths, to commence simultaneous observations of the transient visitor. This rapid mobilization is essential for constructing a comprehensive, multi-wavelength portrait of the object before it inevitably dims or moves beyond the reach of any single instrument's gaze. This level of sophisticated coordination, unthinkable just 2 decades ago, is now becoming routine. Its foundations rest firmly on shared scientific databases, universally adopted standardized alert formats, and robust international collaborations that seamlessly bridge continents and organizations. The future of cosmic discovery lies in this large-scale survey synergy. No single telescope, however advanced, possesses the power to answer every fundamental question about the universe. Instead, the future demands networks of instruments, strategically deployed across the entire electromagnetic spectrum, all orchestrated by automated alert systems. These systems feed their collected data into centralized, publicly accessible archives, enabling researchers worldwide to collaborate and analyze findings instantaneously. This represents a profound paradigm shift. The transition from heroic, isolated solo observations to collaborative, large-scale campaigns that strategically leverage the unique strengths of dozens of facilities operating in concert. The consequences of this transformation are already visible in the accelerating pace of discovery. We are witnessing a surge in detected interstellar objects, a growing catalog of exoplanets, an explosion of recorded transient events, and increasingly detailed chemical maps of star-forming regions. All this groundbreaking information appears in scientific databases faster than any individual researcher could possibly process, fueling an unprecedented era of cosmic exploration. While the 3IATLAS commanded widespread attention with its groundbreaking interstellar chemistry, a quieter yet profoundly significant revelation was simultaneously reshaping our comprehension of near-Earth space. In the month of August 2025, astronomers definitively confirmed the existence of a small celestial body, designated 2025 PN7. This object follows a truly peculiar and highly inclined orbit, one that maintains a loose gravitational connection to our planet. It belongs to a fascinating class known as quasi-satellites, bodies that primarily revolve around the Sun, but, when observed from Earth, appear to orbit our world.
The underlying gravitational interaction is inherently complex, a dynamic three-body problem intricately involving the Sun, our planet, and the asteroid itself. This results in a specific trajectory where the object loops around Earth without ever achieving true capture into a stable orbit like the Moon. Quasi-satellites, while rare within the solar system, are not entirely unprecedented occurrences. At any given moment,
Earth is known to be associated with several such quasi-satellite companions. These are typically small, rocky asteroids, often measuring only a few dozen meters across, which become temporarily trapped in these resonant orbital patterns. The defining characteristic that sets 2025 PN7 apart lies in its exceptional orbital inclination. Its path is tilted approximately 40 degrees relative to the fundamental plane of Earth's own orbit, a stark contrast to the near-flat, ecliptic orbits where most quasi-satellites reside. It is precisely within these lower inclination regions that gravitational interactions with Earth are strongest, making stable quasi-satellite configurations more probable. The pronounced tilt of 2025 PN7 strongly implies it arrived at our neighborhood from an extraordinary angle. This suggests a possible origin within the main asteroid belt, its path dramatically altered after a close encounter with either Mars or Jupiter, whose immense gravity perturbed its original trajectory. This discovery serves as a powerful reminder of the dynamic and ever-changing nature of near-Earth space. Our initial perception often simplistically presents the Moon as Earth's solitary companion. The reality, however, is far more intricate and populated. There exists a diverse population of small celestial bodies gravitationally linked to our planet in various temporary ways. The existence and unique properties of 2025 PN7 illuminate this complex and active orbital environment surrounding our world.
This hidden dynamism directly ties back to the phenomenon of 3IATLAS. It underscores a fundamental truth. Unexpected celestial behavior is far more prevalent than conventional wisdom often suggests. We are accustomed to the remarkable predictability of our solar system's major players, the planets, whose paths, meticulously described by Keplerian orbits, can be calculated centuries into the future with astonishing accuracy. However, introduce small bodies like asteroids and comets, factor in gravitational perturbations from larger objects, consider non-gravitational forces such as solar radiation pressure or outgassing, and the system's behavior rapidly becomes chaotic and unpredictable. Comets, for instance, exhibit dramatic and unforeseen changes in brightness. Asteroids tumble through space with erratic rotations. Quasi-satellites loop around Earth in patterns of such extraordinary complexity that modeling their motions demands sophisticated numerical integration techniques. Furthermore, on rare occasions, an interstellar visitor streaks through our solar system, following a trajectory that originates entirely beyond its boundaries, adding another layer of cosmic surprise. The universe, it turns out, operates with a profound messiness, and the more diligently we observe and study it, the more astonishing and unforeseen phenomena we inevitably uncover. The successful detection of such objects in the year 2027 powerfully showcases the significant advancements in our astronomical survey technology. Systems like the ATR system, known as the Asteroid Terrestrial Impact Last Alert System, utilize multiple wide-field telescopes to scan the entire sky each night. Their primary mission is to search for moving objects that pose a potential collision risk to Earth. Designed specifically to identify asteroids on orbits that cross paths with our planet, this dedicated surveillance network, however, inevitably discovers other celestial phenomena as well. Its powerful gaze captures distant comets, identifies quasi-satellites, and, as demonstrated by the discovery of 3IATLAS itself, can even detect rare interstellar objects venturing through our solar system. As advancements in observational technology accelerate, a new era of celestial discovery unfolds. Telescopes grow ever more powerful, their mirrors spanning vast distances to capture faint light, while detectors become increasingly sensitive, able to register photons previously lost to noise.
This technological synergy fuels an unprecedented surge in astronomical findings, with hundreds of previously unknown asteroids now cataloged each passing month. Every new specimen contributes vital fragments to our understanding of the solar system's myriad small bodies, revealing patterns and histories inscribed in rock and ice. A particularly intriguing phenomenon involves objects known as quasi-satellites.
These celestial companions maintain a complex gravitational relationship with our planet, remaining linked for astonishingly long durations, decades, and occasionally even centuries. Their paths, when visualized in three-dimensional space, form intricate patterns resembling tangled knots. One such object, PN7, exemplifies this peculiar existence. Astronomers estimate it will likely remain in this resonant embrace with Earth for 50 to 100 years before subtle gravitational nudges from other bodies disrupt its delicate balance, sending it drifting away into the solar expanse. During its extended stay, PN7 will execute a remarkable routine. It will loop around our world multiple times annually, yet maintain a consistent distance of approximately 20 million kilometers. This places it firmly within the gravitational influence of Earth without ever crossing the threshold into a true, captured orbit. Conversely, it remains securely tethered, never venturing far enough to break free entirely. This perpetual state of suspended animation constitutes a cosmic ballet choreographed precisely by the intricate dance of gravity, a spectacle occurring silently in the vastness of space, observable only by chance if astronomers direct their instruments toward the correct quadrant at the opportune moment.
Consider the scenario. If one possessed the motive and capability to study a planet known to be inhabited, yet desired absolute secrecy, deploying a surveillance probe into a quasi-satellite trajectory would constitute a remarkably discreet tactic. Such an orbit, locked in gravitational harmony with both Earth and the Sun, could allow prolonged observation without easily betraying the observer's presence. Future astronomical investigations promise to definitively clarify the provenance of the object designated PN7, determining whether its provenance stems from capture within our solar system's main asteroid belt or presents a more tantalizing prospect, a surviving fragment cast off from an interstellar traveler passing through our cosmic neighborhood, hinges on compositional analysis. Sophisticated spectroscopic techniques will meticulously examine PN7's light, decoding the unique signatures it absorbs and reflects to reveal its fundamental makeup. This crucial data will indicate if PN7 consists of commonplace silicate minerals typical of solar system bodies, or if it harbors signatures of more exotic extraterrestrial origins. Simultaneously, precise photometric measurements will track the object's subtle rotational behavior over time, searching for telltale variations that might hint at internal structure or surface features. Should these analyses uncover any deviation from the expected norm, a chemical signature or physical characteristic differing significantly from established solar system objects, it would undoubtedly deepen the enigma surrounding PN7's identity and history. However, the most probable outcome, grounded in the vast majority of known asteroids, is that PN7 proves to be entirely conventional. It likely represents an unremarkable, stony fragment, an incidental visitor that simply drifted into a temporary, resonant gravitational embrace with Earth, remaining in quasi-satellite lock for a fleeting cosmic moment before continuing its solitary journey through the void. Nonetheless, the very fact that humanity has reached this point, capable of detecting such elusive objects, precisely characterizing their properties, and confidently mapping their intricate paths, serves as a powerful testament to the extraordinary advancement in our observational prowess. This capability directly connects to a much larger, profound theme in modern astronomy. The seemingly empty regions beyond our atmosphere, particularly the fringes of our detection power, are demonstrably teeming with unforeseen surprises and complex phenomena. Each incremental improvement in telescope sensitivity acts like sharpening our eyes, revealing fainter and fainter objects.
Every new, more comprehensive survey that sweeps the sky with greater thoroughness consistently uncovers celestial bodies and events previously unknown to science.
Quasi-satellites like PN7, interstellar comets making fleeting visits, Trojan asteroids stably orbiting at Earth's Lagrange points, and even objects traversing their orbits in directions opposite to the planets. These are not isolated curiosities, but pieces of a much richer, more intricate, and dynamically active solar system than astronomers of the mid-20th century could have envisioned within the confines of their textbooks. If our own immediate stellar neighborhood continues to yield such astonishing revelations, what profound secrets might lie dormant within the vast expanse of the galaxy itself? Many potential wonders remain shrouded in silence, too dimly luminous or too remote for the grasp of our present technology. Yet they stand tantalizingly close, poised to be unveiled by the advanced instruments of tomorrow. Let us now synthesize the various elements that weave this intricate narrative: chemistry, geometry, enigma, and the subtle art of coincidence. The hydroxyl signal originating from a star system designated as ATLAS fundamentally revealed chemistry manifesting beyond our own solar system. It depicted the process where water molecules dissociate under stellar radiation, their liberated components then propagating a celestial broadcast, traversing distances measured in hundreds of millions of kilometers. The precise geometry governing the object's trajectory, coupled with the exact moment of its detection, underscored the extraordinary rarity and immense value of such an observation. It represented a fleeting temporal aperture, a confluence of conditions where all factors aligned perfectly. To attempt observation even a fraction of a year earlier or later would have resulted in the complete absence of this vital signal. The persistent anomalies observed in its behavior, deviations from predicted paths, peculiar formations in its tail, fluctuations in brightness, serve as a powerful reminder that natural celestial bodies can exhibit actions profoundly challenging our established scientific models. Furthermore, the circumstance of its position being noted near a previously detected signal region, whether this proximity held inherent significance or was merely serendipitous, effortlessly captures the human imagination. We as a species possess an innate drive to discern patterns, to crave the notion that the universe is endeavoring to communicate a message to us. But perhaps a more profound perspective emerges. The universe itself functions as a vast communicator, not in the anthropocentric sense of messages explicitly directed at our species, but in the deeper, more fundamental sense that every entity within it inherently carries information. Every single photon emitted encodes the precise physical conditions of its point of origin. Every distinct molecular absorption line serves as a unique fingerprint, revealing details about the temperature and density of the surrounding environment.
Every celestial orbit, in its intricate path, traces a historical record of gravitational interactions experienced throughout cosmic time. The cosmos, therefore, is fundamentally not silent. It is a continuous, intricate flow of information, patiently waiting to be deciphered. Here is the deeply reworked narrative, faithfully expanding upon the original concepts with enriched language and seamless flow. The universe, in its boundless reach, transmits an unceasing symphony. This communication occurs across every conceivable wavelength and manifests at every scale, from the infinitesimal to the cosmic. Our fundamental challenge lies not in the mere detection of these faint cosmic signals, but in the profound act of deciphering their meaning. It demands the development of sophisticated instruments, the cultivation of novel theoretical frameworks, and the mastery of a unique language, the language of the physical universe itself. Perhaps the cosmos has been murmuring its secrets all along. Only now, through immense scientific endeavor, are we finally attuned to listen. The celestial body, designated 3IATLAS,
notable for its hydroxyl emission signature and enigmatic behavior, stands as a singular example. It is not the inaugural interstellar traveler to have transported the essential building blocks of life, water and complex organic molecules, through the expanse of our solar system. It represents, however, the first such visitor whose passage we have successfully identified. How many others have traversed the void between the stars, unseen and unremarked upon? How many more will our enhanced capabilities reveal in the years ahead, as our observational instruments grow ever more sensitive and our surveys encompass greater swaths of the heavens? And what profound knowledge will these distant messengers impart? These wandering icebergs, originating from suns beyond our own, hold clues about the galactic distribution of chemistry and offer tantalizing insights into the potential for life scattered throughout the Milky Way. The narrative of 3IATLAS transcends the story of a single comet following a specific trajectory. It is instead the story of a species awakening to its potential as cosmic interpreters. It chronicles our journey in developing the very technology and conceptual tools necessary to translate signals we could scarcely have envisioned a mere century ago. Consider the progression. Radio telescopes, tuned to capture the faint whispers of molecules drifting through interstellar space. Optical surveys, meticulously tracking the minute shifts in position of distant objects as they traverse the celestial sphere. Infrared instruments mapping thermal landscapes on worlds located light-years from our own. Pulsar timing arrays measuring the subtle ripples within the very fabric of space-time itself. All these distinct endeavors are converging, each contributing a vital piece to the cosmic puzzle.
Collectively, they are unveiling a universe far more intricate, vibrant, and profoundly stranger than we dared imagine possible. Their revelations redefine our understanding of existence, and perhaps, just perhaps, there exists the tantalizing possibility that one day we will detect something within the vastness of space that defies explanation by natural processes alone. Here is the deeply reworked, expanded narrative in elegant English prose. The universe whispers in a language our minds are only beginning to decode. It might manifest as a signal possessing a structure too rigid to be mere chemical reaction. It could appear as a trajectory possessing a precision too exacting to be explained by gravity alone. Or perhaps it would reveal itself as a pattern displaying a regularity too perfect for the chaos of the cosmos to naturally produce. Should such a phenomenon ever emerge, and we are certain that if it does, we shall be prepared. We have constructed the sophisticated instruments capable of detecting its faintest trace. We have refined the techniques necessary to analyze its every nuance. We have gained the critical ability to separate genuine cosmic signals from random noise, to distinguish fleeting coincidences from underlying causation, and ultimately to transform profound mystery into tangible understanding. Until that potential moment arrives, our role remains one of patient vigilance. We listen intently, our instruments attuned to the deepest reaches of space. We watch relentlessly, scanning the vast expanse of the night sky. We catalog meticulously every faint whisper emanating from the profound darkness, every anomaly detected within our complex data streams, every celestial object whose characteristics suddenly defy established models. For somewhere within this overwhelming flood of information, somewhere within the terabytes of spectral analyses, astronomical images, and precise timing measurements, lies the potential answer to the oldest and most fundamental question our species has ever pondered. Are we truly alone in the universe? The discovery of 3IATLAS did not provide a definitive answer to this age-old query. However, it illuminated our path forward.
It taught us where to direct our search, not towards deliberate broadcasts or obvious cosmic beacons, but rather into the intricate realm of chemistry itself. It pointed us towards the molecules that traverse the immense gulfs between stars, and towards the ice and complex organic compounds that might one day seed nascent worlds with the essential ingredients for life. The next interstellar visitor, and the one following it, and the hundreds or thousands that the Rubin Observatory will identify over the coming decade, will each yield invaluable new information. Each comet represents a single data point, a crucial piece of evidence. Each discovery refines and deepens our comprehension.
Each one brings us incrementally closer to knowing whether the specific chemistry we detected in 3I-ATLAS is a common occurrence throughout the galaxy or a rare anomaly. It brings us closer to understanding whether the fundamental building blocks of life are scattered abundantly across the cosmos or exist in profound scarcity. It brings us closer to discerning whether the universe is indeed teeming with potential voices, civilizations whose communications we are only now learning to perceive and interpret. The signal emanating from 3I-ATLAS gradually faded and ultimately disappeared as the comet slipped behind the sun, vanishing once more into the profound and eternal darkness of interstellar space. Its departure marked the end of its immediate observation, leaving behind a legacy of questions and a renewed determination to continue the search. The celestial traveler, now forever lost to our gaze, accelerates into the cosmic void at a velocity of 42 kilometers per second. It carries within its frozen heart the elusive chemistry it still preserves, journeying inexorably towards a distant stellar system. Its arrival there, however, lies buried in the distant future, a million years hence. Humanity, for a fleeting instant, had opportunity. A narrow window of convergence where celestial geometry and human ingenuity momentarily aligned. Through this aperture, we captured a profound signal, the distinct signature of hydroxyl radicals fragmenting under the distant light of a foreign star. We meticulously measured the velocities and line widths of this cosmic echo. And so, for the very first time in the annals of human history, we confirmed that water, the essence of life as we know it, originating from another star system, resonates with an acoustic signature identical to that of our own terrestrial waters. Now we enter a period of patient anticipation. For such icy wanderers, countless in number, drift silently through the star-studded darkness. And sooner or later, inevitably, another will draw near enough that our instruments can again perceive its whisper. When that moment arrives, we shall be prepared. Our telescopes remain vigilant, tracking the heavens. Sophisticated algorithms continuously process the endless stream of cosmic data. The instruments stand poised, attuned to every faint vibration emanating from the cosmos. They transform the language of chemistry into profound understanding, decode the history written in motion, and render the fleeting signals into compelling narratives. And perhaps within one of those nascent stories, born from the silent exchange between starlight and ice, lies the revelation we have pursued since the dawn of consciousness, since the first curious minds gazed upwards into the night and pondered the profound question, who else somewhere in the vastness might be listening?